All right, example 3, understand stretches and compressions. So again, if I stretch something, I can either stretch it this way, so vertically, or I can stretch it horizontally, or I can compress horizontally, or I can compress vertically. Okay, so I can make it shorter, I can make it bigger. Okay. So I'm looking at graph f of x equals the absolute value of x with domain -4 to 4, and g of x equals 2 times f of x. How are the domains and ranges related? So looking at these two graphs, so here the blue is my absolute value of x, okay? Then I'm going to multiply that times 2, which gives me this orange one. So the original points that I had were -4, 4, -2, 2, 0, 0, 2, 2, 4, 4. What I did was I multiplied each one of these by 2 to get my new points. So my x value stayed the same, but my y values essentially changed, okay? So looking at this, the domains of f and g are the same, okay? So I'm going from the same spots, okay? Each y value is multiplied by 2, so for the function with the given domain, the range of f, 0 to 4, is doubled for g, okay? So I multiplied it by 2, my range went up to 8. Okay. A transformation that increases the distance between the points on a graph and a given line by the same factor is called a stretch. So looking at this, I stretched my function. Okay. The graph of g is a vertical stretch of the graph of f by a factor of 2. So I multiplied by 2, so I got a vertical stretch. B, graph f of x equals the absolute value of x with domain -4, 4. And h of x equals f times 2 of x. How are the domains and ranges related? So looking at this, so absolute value of x and absolute value of f of 2 of x. So I multiply what was inside. Okay, that's how I got these values. So I shrunk it, I compressed it down. Okay, so I made it smaller. I squished everything together. Okay. For each corresponding output, the value of the input for h is half the value of the input for f. The two functions have the same range, but the values in the domain of h, -2, 2, are half as large as the values in the domain of f, -4, 4. A transformation that decreases the distance between the points of a graph and a given line by the same factor is called a compression. The graph of h is a horizontal compression of the graph of f by a factor of 2. So looking at this, again, my blue line is my original function. I multiply what was inside the x values by 2. So it compressed it. If I multiply my y values by 2, it stretches it. If I multiply my x values, it compresses. So be careful not to assume that the domain of a transformed function is the same as the domain of the original function. Notice that h, -4, would equal f, -8, which is outside the domain of f, -4, 4. And just a comment here. All right. Show that j of x equals f 1/2 x is a horizontal stretch of the graph of f. You can use the table to help you. Okay, so I'm multiplying each of my x values by 1/2, so -4 times 1/2 is -2. -2 times 1/2 is -1. 0 times 1/2 is 0. 2 times 1/2 is 1, and 4 times 1/2 is 2. Okay, so if AB is the domain of JX equals f 1/2 x, then JA equals f 1/2 A, and JB equals f 1/2 B. So 1/2 A, comma 1/2 B is the domain of f, since, okay, so again, we took each of these and we divided by 2, multiplied by 1/2. Since AB equals 2, 1/2 A, 1/2 B, domain of F is stretched by 2 to create the domain of J. Okay. I can also graph this to kind of show you what it is. Okay, so J, so this is a parabola, so, okay. So here, my original is the green, and then I stretched it because I multiplied my values by 1/2, so it got stretched. Okay. So again, concept, stretches versus compressions. So vertical, we can look at a stretch when K is greater than 1, that's that red. Compression when when K is between 0 and 1, that's that blue line. The black line is the original. Okay, same thing for horizontal. You can see it stretches out further. All right, example number 4, graph a combination of transformations. So the graph represents y equals f of x. Using y equals f of x, how can you graph a combination of transformations? So A, graph y equals negative x plus 2. Okay, so I'm going to graph g of x equals f of x plus 2, which is a translation of f left 2 units. Okay, so here's my original graph, and I wanted to change everything 2 units to the left, so I just moved that point 2 units to the left. I moved this top point right here 2 units to the left. I moved this point 2 units to the left. I moved this point 2 units to the left. So all I did was I picked points and I moved them 2 units to the left. Okay. Then I graphed h of x equals negative f x plus 2, which is a reflection of g across the x-axis. So basically I took g and I flipped it across the x-axis. So this was 2 points away from the x-axis. So this is 2 points away. This is 1, 2, 3, 4 points away. So this is 1, 2, 3, 4 points away. Okay, so that's all you have to do for that. The graph of h is a translation of f left 2 units and then reflected across the x-axis. Okay, so it's kind of like a game of Tetris. If you ever play Tetris, like this is how you move pieces and you have to like rotate them and things like that. That's what you're doing here. Okay. So the graph represents y equals f of x. So here's my graph. Using y equals f of x, how can you graph a combination of transformations? So I want to graph y equals 1/2 f of x plus 3. Okay. So the first thing that I want to do is I want to move it either vertically or horizontally, and then I want to either stretch or compress it. Okay. So the first thing, that plus 3 tells me that I'm going to move to the left. Okay. I did a vertical compression first. So they graphed g of x equals 1/2 f of x, which is a vertical compression of f by the factor of 1/2. So they basically took each of the points and they divided them by 2, or multiplied by 2. So this point right here, divided it by 2. So this was at 2. Now it's at, this was at negative, this was at 2, now it's at 1. This was at 2, 3, 4, now it's at 2. This one was at 3, now it's at 1.5. This point was at 7, now it's at 3.5. Okay, so they just took each points. And then h of x equals 1/2 f of x plus 3, which is a translation of g up 3 units. Okay, so they took that compression and then they moved that compression up 3 units. 1, 2, 3. 1, 2, 3. 1, 2, 3, 1, 2, 3. Okay. All right, here is the try it. Using the graph of f, graph the function y equals f 2x minus 4. Drag the points to transform the graph of f. So the first thing that I want to do is I want to compress this. So by 2, and everything's going to be this way. Okay. So this is 1, 2, 3, 4. So now this is going to be here. Okay, this is 2, so this is going to get moved 1 over. Okay, this is going to get moved right here in the middle. This is going to get moved right here in the middle. Okay, and then everything's going to get moved down 4 points. So this goes, it's a little smaller. So 1, 2, 3, 4 gets moved down here. 1, 2, 3, 4. One, 2, 3, 4. And then 1, 2, 3, 4. And we can check it. It's pretty close. Okay. Do the same thing with my next try problem. All right, using the graph of f, graph the function y equals f times the quantity 2x minus 3 minus 2. So this is a compression of 2, and then we move it down and we move it over. Okay, so lots of things are going to be happening here. I want to focus on what's inside the parentheses first, so I can drag the points to transform the graph of x. So the first thing that I want to actually do is I want to rewrite this. So this is what I actually have, but I want to rewrite this as 2x minus 1.5. Minus 2. This is minus 2. Okay. I can basically take 2 out, and now I have the x minus 1.5. Here's my compression, this 2 right here. And then the minus 1.5 tells me I need to move it, and the minus 2 tells me I need to move it. Okay? So I want to do a compression first of 2. Okay, so doing that, I can compress it by 2. Okay, so there's my compression. The minus 1.5 tells me to horizontal shift to the right 1.5 units. So this is 1.5. 1.5. 1.5. And then 1.5. Okay, so then I want to move it down 2. Let's move everything down 2. 1, 2. 1, 2. 1, 2. Oops, 1. Okay, so here's my new points. Check my answer. That's what it is. Here's my answer. Okay. All right, then I have example 5. Example 5 says identify transformations from an equation. So what transformations of f of x equal x squared results in the graph of the function g? So I have the blue, and I'm looking at the red. Okay, so my graph is, okay, so here's x squared result in the graph of the function g. So g of x equals negative 1/3 x squared. So that tells me that it is a reflection over the x-axis, and it tells me this 1/3 tells me I stretched it out. So you can see that I stretch. Okay. So f of a third x equals 1/3 x squared. So that's, again, that's that stretch out. okay? And then because it's negative, that tells me it flips over the x-axis as a reflection. Okay, looking at this graph, x squared. I have x minus 4 squared plus 5, so that means it moved over 4 to the right, and it moved up 5. So this moves over, this moves up. So at 4 units to the right, 5 units up. Okay, so now I have a try problem. What is the transformations of the graph of f of x equals the absolute value of x are applied to the graph function g? G of x equals 1/2 x plus 3. So again, I can graph these, so I just see what they look like. Y equals absolute value of x, and y equals 1/2 times the absolute value. X plus 3, 1/2 times the absolute value of x plus 3. Okay. So looking at this, I can see that the graph shifted 3 units to the left, and it stretched, okay, it got wider basically by a value of 2. Okay, so the graph shifted 3 units to the left, and it stretched by a factor of 2. Okay, sorry, compressed by a factor of 1/2. All right, g of x equals the negative absolute value of x plus 2. So I can graph that one. Equals negative absolute value of x. Oops. Negative absolute value of x plus 2. Okay. So again, I can see all I did was, there's my negative x, negative absolute value of x, so that flipped over the x-axis, and that plus 2 moved it up 2. So the graph reflected across the x-axis and moved 2 units up. Okay, translated 2 units up. Okay. So again, it is really helpful to draw a lot of these graphs if you can. I highly recommend Desmos, desmos.com. It is free to use. You should be able to access it on all your Chromebooks. All right, example number 6, write an equation from a graph. A scenic train ride makes trips on an old mining line. The graph shows the distance y in kilometers of the train from the station x minutes after the ride begins. What equation represents the distance from the station as a function of time? What is the domain? Okay, so looking at this, it comes at a point, so I know it's going to be an absolute value function. It is facing down. Okay, not up, so it is going to be a negative absolute value function. And the top, it shifted over. Usually my absolute value function starts at 0, 0. So it shifted over to 15, and it's at 15. Okay, so the graph shows a reflection. We just talked about that. General form of this absolute value function is y equals negative a times the absolute value x minus h plus k, where the point hk represents the vertex and negative a indicates that the graph opens downwards. Okay, so I know that that point, that vertex is 15, 15, so minus 15 plus 15 respectively. Okay, so I just substitute those values in. To solve for a, you can use any point on the graph. Using the point 0, 0 to substitute for x, y in the equation simplifies the computation. So nice. Always use 0, 0 when you can. Okay, so I substituted in 0 equals negative a times the absolute value of 0 minus 15 plus 15. 0 minus 15 is, of course, negative 15. Absolute value is 15. There's a negative out front. So 0 equals negative 15a plus 15. Negative 15 equals negative 15a. So I divide both sides by negative 15. A equals 1. Okay, so that means that my graph, y equals negative absolute value of x minus 15 plus 15. According to the graph, the train returns to its station after 30 minutes, so the function's domain, looking back here at my function, is 0, 30 domain. Okay, remember, range is your y, domain is your x, your time, in this case. Okay. All right, number 6, the try it problem. How would the graph and equation be affected if the train traveled twice as far in the same amount of time? So it's traveling twice as far, so it's going twice the distance. So that means it's going to be, so here's the distance, that means it's going to be 1530, right? So that means there'll be a vertical stretch a factor of 2, because it's doubled, twice as far, doubled it, okay? So the new equation would be d equals 2 negative m minus 15 plus 15, or negative 2 m minus 15 plus 30. Okay. So again, the time didn't change. That 15 is still the same, but I doubled my distance. So I go from 1515 to 1530. That's where I got that 30 from. And then this 2 is going to tell me that it's going to stretch. Habits of mind, make sense, and persevere. The function f of x equals the absolute value of x is translated 3 units right and 2 units down, and then stretched by a factor of 4. What's the equation for the transformed function g? Okay, so I'm translating 3 units to the right, 2 units down. Okay, so g of x equals the absolute value of x plus 3, no, x minus 3, sorry, okay, and 2 units down minus 2. And it's stretched by a factor of 4. So I'm going to multiply all of that times 4. So g of x equals 4 times x minus 3 minus 8. All right, concept summary, transformational functions. So horizontal translation of f, right 2 units. Okay, so I just add, so really I subtract that. I'm going right, okay? So that's inside the parentheses or inside the absolute value. If it's going up or down, it's this outside one. So inside is horizontal, outside is vertical. Reflection across the x-axis is a negative function. Reflection across the y-axis, the inside is negative. The horizontal stretch, so a factor of 1/2, vertical stretch, outside. So inside's horizontal, outside's vertical. Same here. Inside's horizontal, outside's vertical. Okay, so that's probably something that you can remember. Inside's horizontal, outside's vertical. Okay, if you're multiplying, it's a stretch or a compression. If you're adding and subtracting, it's a horizontal shift or a vertical shift.